This is a talk about the ELF binary format. So also you will see C++ 11 code. It's not about Elvenland. And also you will see odd and even numbers. It's not a talk about even land, right? That's what happens when you're French and you try to make English puns. So, welcome to my talk. This is one of the talks where you won't see any metaprogram. You won't see any context stuff. You will see only low-level aspects of the language, or exactly low-level aspects of what the language generates. Before we move on, let me introduce myself. So I work in a security firm in France. I'm an R&D engineer there, working on an obfuscating compiler. So by force, I had to interact with these aspects. And so I try to share what I learned. So I'm not an embedded developer, so that's not my daily task, but I think I have some extra knowledge you would benefit from. I'm also a researcher, LLM committer, and a developer of a Pythran to C++ translator, but it doesn't matter for that talk. Okay, so to welcome you in a proper way to that, I should say Helen Sila Lumen, Umen Tielvo, right? So this is a trip in the land of elves, with a focus on old artifacts, ancient artifacts. Some of them come from C, some of them come from before C, and some are really specific to C++, or are already used in C++ and not in C. So it's a mixture of C and C++. So if you want to know the origin of elves, the true origin of elves, you have to read that book. And you will learn that elves come from the song of a great being. But we computer scientists are not very respectful of the ancients. For us, wyvern like LLVM or objd, or even a GNU can give birth to elves that get along very well with dwarves. And that's what we are talking about, right? So executable and linkable format. So it's mostly used in the Unix world. Any object file, core file, share object, or executable you're manipulating, if you're on Linux, is an ELF. We're going to dig about that. But we are starting from the beginning. C code, the simplest one, and you're compiling it, right? Let's ask file what this kind of file is. And it's very verbose. Instead of just stating this is a binary, it tells you a lot about it. So it's an L format, 64 bits, position independent, for a specific architecture, for a specific specification. It's dynamically linked with some kind of interpreter. I didn't know that C was interpreted, but it looks like so. It's for GNU Linux. There is a build ID, and it's not strict. Let's enumerate all that. There are actually two different possibilities of being an elf. It can be a very tall elf, 64-bit elf, or a smaller elf, a 32-bit elf. And depending on your size, you can be very big and address different memory. So there are two possibilities of being an elf. And there is also this little Indian, big Indian stuff, and it's hard-coded in the header. Then you can love pi or not. If you're position independent, then your binary can be loaded at any position in the virtual memory, and that's pretty good for ASLR. So from a security purpose, if you're pi, that's good. So you're using an instruction set, so you have some extra information about my laptop, and there's only one version of the ELF format anyway, but still it exists. It's prepared for the future. The future never happened. When you're a binary, you have to respect a lot of conditions, what's called the binary interface, and this ELF respects the System 5 ABI. So it tells you about something about the object formats, how you call it, how you call functions, a lot of stuff. And we are respecting that, advertising that. It's dynamically linked. We call the putS function. So it has to be somewhere. And there is this interpreter, which is actually not an interpreter for the binary, but just a loader. Okay, some kind of linker that does all the things that were not possible at link time are done just before running the executable, but we're going to elaborate on that. We could have generated a static version of this binary. If you have a look to LDD, it tells you that for the file I compiled, I'm using all this library. So this one is a bit special. It's a wrapper for kernel functions that are exposed in userland. You can have a look at the manual. I won't explain on that. We've got the libc and this loader. But I could have compiled with the minus static flag. And in that case, file would be much less variables, stating me that I'm statically linked, no interpreter anymore. And if I look up for all the dynamic library I'm linked with, it's not a dynamically linked executable. Okay, so dynamically linked executable or static executable, and you can choose that upon compilation. Obviously, the second one is much larger than the first one because it's embedding part of the libc into its file. So if we move on to the header, we also have an IBE for the libc we are using. So this is the GNU Linux version, but we could be using other ones. We also have this build ID. I was not aware of that. A build ID is some kind of hash, which you are not supposed to be able to reproduce. It basically hashes the text section, the data sections, and give you a number. But for maintainers, say Red Hat maintainers, if you submit them a core file, they have this build ID, and they can just look up in all the binaries they have produced and say, okay, this has been produced by this binary. Okay, so it's just an identifier for your binary. It's easier to upload these identifiers than the whole binary. And it's not stripped, which means that it still has some symbol information, eventually debug information, but we did not compile with -g. And that's how it is. We could have access to all this information using readelf. Readelf just minus header, just decodes all this information, the same as file, and give you some extra stuff. The only thing I want you to look up here is, in addition to all this metadata, you have also information about sections. Okay? And file told us that this binary was not stripped. We could strip it. Strip it means removing symbols and removing debug sections. If we do that, and we readelf again, then the number of sections has decreased. We have been removing some part of the file, but it does not prevent it from running. Okay? We are just changing the file, but without removing the important parts, or the parts that are important for the execution step. So we've been removing the symbol table, and it doesn't matter. So what is a symbol table? If you use objdump -t, you have all this information. A symbol table is just what would be a global variable in your C++ program, or a function, which is also something with global visibility. But we did not define all of that. We defined main, and it's here. We used putS, and it's here, and we've got all these things. They are used internally, sometimes to manage initialization, sometimes to manage constructors at static time, and sometimes to give you addresses on some part of the program. Some of them are undefined, which means we need this symbol, but we don't know where it is. So that's for putS, because it's in the libc. Sometimes it's in the code, in the text section, that's for main. And there are plenty of other sections. We are going to go through some of them, not all of them. And I would not be able to explain every symbol here anyway. So this ndef, putS is ndef because it's in the dynamic symbol table. In the dynamic symbol table, you say, okay, I'm a binary and I need this symbol, and the linker has to find it somewhere. All these symbols are needed to run the program, but they are not in my binary. Indeed, if I have a look to the dynamic symbols of the libc, the very same one I had with LDD at the beginning, and I grep for putS. Then I got my symbol, and they match. Okay. So when you've got a link error, it's because there is a mismatch. LD, or the dynamic loader, is some kind of Tinder for symbols. Okay. You need to have a match between the two. So first step, what we have learned. So ELF is a binary format. There's a header with a lot of informations, and we've got sections, and each of these sections holds symbols, and there is nothing specific to C++ here. Okay, let's move on. Talking about low-level stuff is not very entertaining, so I'm trying to add some bonus, some stuff you could do now that you understand what happens. It may not be very relevant to your daily life, but this particular example may be. You've got an image, and you want to embed it into your application. There is different possibility. Either you're in the Windows world, and you've got these resources stuff. But if you're in the Linux world, you could use XDD and generate a C array that contains the very same bits as this image, and then you embed that into your application. But that's an extra compilation step. It may not be that portable, or you have to commit the header file into your code. Or you could use your new command of ELF. So what you tell, obfcopy is a tool to manipulate ELF formats. So you just say, my input has a binary information I don't know much about. You give it false information about its language. It doesn't matter, but you just tell, put that image into an object file, which has an ELF format. And then if I objdump this newly created object, which has nothing to do with assembly code, you've got a data section, so it's okay, it's not code, it's not a text section. And you've got a few symbols that tells you the start, the size, and the end of this section. So now you can just use a void star pointer to that section and address it and load your image. It's actually already loaded. So it's free. You don't need to load it from the file system. It has been loaded as part of loading your application. You know, even with low-level stuff, you can do things that are actually useful in your application. So it's capital ELF, because you're dissecting it, right? So you've got this header, and this header have pointers to different sections. The text sections, the read-only data sections, the data sections, and a few other stuff. But actually, there are two views. There's one view, which is the one I gave, and there is the one that the linker has. And the linker doesn't care at all about sections. What's important for it is segments. And the segments, from my understanding, is just a bag of sections, right? So the sections are not very important for the linker. It just needs to know which code area it needs to load somewhere. We could have a look to the segments of our hello program. And so they are numbered, and each segment maps to several sections, right? So let's talk about symbols. Here, we are in C++. So we are going to have much more symbols than in C, but that's expected. We compile these hello words, and then we use nm instead of objdump, but that's roughly the same, on our generated program. And we've got all these symbols. So this is the address, this is its type, right? And this is its name. And you may be aware that this name is not the one you expect for std.io base init. This is not std.io init, so it's mangled. It's mangled because it has to live with C symbols too. So they need to get on together, but they can't speak the same. So that's why there is this specific thing. And you're not supposed to write that in C because it's underscore and a capital letter, so it's reserved. So it's foolproof. if you have to demangle it, then it's okay. You understand it back. And demangling is important because of overloads, namespace, and this stuff. But you can have fun with mangling. If you don't respect the standard, you can write this C++ code. So foo is marked as extern C, which means using C mangling on it. And as you are using C mangling on it, you can't have overloads because mangling is used to distinguish overloads. So you don't have overloads for that. Then you've got foobar, a regular C++ function, which is not defined in this file, and bar that calls alts, so just so the symbols are not removed by the compiler. I compile that, and I have my foo function, not mangled. It's okay, it's extern C. And these two functions that are mangled, first one is defined. It's in the text section, capital T, at some address, and the other one is undefined. It's not in this file. And now I will write a C file. And this C file will resolve for foo, that's okay, but also for foobar. To do that, I just need to compile my C file and explicitly use the demangling address strategy, and that will compile fine, and it's okay because they only match based on their name. And so if I provide the right name, it works. So that's not standard compliant. That's not very useful. That's not even portable because the mangling is not it's dependent on the ABI. And so it may not work on Windows, for instance. So you don't do that, but you know you can do it. So constant symbols. We expect them to go into the read-only area. And those are very simple symbols. I compile them, and I'm looking for symbols, and I find nothing. Why? Maybe they are in the dynamic area. No. Where did he go? It turns out that those are const symbols. So their default linkage is not global. It's static. And they are not referenced anywhere. And so in my contrived examples, it just disappeared because they are never used, and so they don't need to be emitted. So you forced them to be extern, so that a symbol will be actually generated, and then I get my symbols, and they are in the read-only data sections. Okay? I was not aware of that rule when I wrote the slide, but because generally, when you write constants, you use them. But anyway. So, symbol conflict. Every newcomers have symbol conflicts. So, but now we will understand why. We have two files, no inline 0 and no inline 1. And you've got bar 0 and bar 1 in the different files, so they won't conflict. But you're defining foo function in both. I'm compiling both of them separately, so I've got these two object files. And then I'm trying to create a shared library that contains everybody. And you've got this very famous error. Okay, multiple definition of whatever symbol, and it first defined somewhere. And let's imagine Tinder gives you two match, and you all meet in the same place. Okay, that's what happens. You don't want that, correct? But now you understand it's very simple. You just take the symbol table and you see if they match or not. But there is this inline keyword. To my opinion, it's an yield name keyword because the compiler, it's just an int. So it doesn't give you any guarantee about the inliner behavior. But it has a side effect, which is actually the only predictable effect of inline. If you mark the both foo function inline, you can compile them separately, generate your shared library, and you don't get any error. Why is that so? It's because they are marked as weak. Because inline function tends to go into the header. And so they are reproduced in every object file. And so they need to match. So when you're weak, you can date several people. Yeah, question. I have the answer in the next slide. So the question was, if we had two shared library, each one with a weak symbol named the same, what happens? Is that your question?
No. If we compile one of these sources and create a dynamic library, we have one symbol with T and one dynamic.
Oh, so if a weak symbol meets a normal symbol, it happens exactly in the same as in the real life. The weak one disappears. And I have an example of that. You're probably aware that if your method is declared inside the class, then it's inline. It's actually not inline. It has the same storage. It's also weak. So this is why you can declare your methods into your object file, into a header, and it still matches. So that's actually the ELF support for the one definition rule. You've got different weak symbols, and one of them will be picked, one of them, and you have no guarantee about which one. So you're thinking, okay, so if I want to change the behavior of a class, I may have a chance by providing my own object, which is not weak, and it will override the behavior of the previous one. So we've got a clever way of changing the behavior of a class that is defined in a shared library. If it's weak, then you can change it. But you're not supposed to do that. A funny thing, just out of curiosity, I was looking for malloc. I wanted to say malloc is weak, and so you can provide your own malloc allocator. It turns out that on my laptop it's not. On my system it's not. But random is weak. Okay, it's opening a lot of possibility. You can redefine your own random number generator. Like you define a random function that always returns 6. You don't mark it as weak. You link with the libc, and your random number generator will be used instead of the one of the libc. Or you could put that into a shared library. Okay, so anyone linking with your shared library will be using your random version without any conflict because it's weak. So in C++, you've got name mangling, and it's very important for namespace and overloading. Depending on the keyword you're using, static or inline, you get different visibility for your symbol. And one definition rule and inline imply weak. That's the important stuff. So that's my custom number generator. Okay, I create a static version of random. I don't have any conflict, and that works. Both static and dynamic. There's no conflict. That's great. I have also this very contrived example, but it's actually very cool. So let me elaborate on that. So it's not standard. It's using a specific attribute, which is supported by GCC and Clang. So I have this pop symbol. I don't give its implementation. But what ELF says, or maybe System 5 ABI, I don't know, is that if I have a weak symbol which is not defined, then it's null. Okay? So I can have a different behavior in my program depending on what I'm linking with. Okay, maybe I'm linking with a threading library, and so in that case, I need to be more careful. But if I don't link with a thread, I don't need to be careful, so I can do different stuff. So this is a way to detect whether your code is linked with a dedicated library or not. So for instance, if I just compile that and execute it, I've got hello. So that's not hello with pop, because pop is undefined, but it doesn't matter because it's weak. It really doesn't have to be weak. But if I am compiling with a pop library, which defines this pop symbol, then I have hello with pop. So just a small bonus. Here I had this linker flag minus rpath dot. And this means that when I am looking for new libraries, I will look into the current directory. And I can get this information from the dynamic section. Here I have this run path. Yeah, sometimes it's useful if you want to fix your library dependencies. Okay, let's move on. The three most important sections. The text section, that's where the code lives. Okay, so my hello, my main symbol is in the text section. It's defined somewhere. And the text section has its proc bits, so code. It's executable, fortunately. And it's taking size when loaded in memory. That's what halloc means. Then I can define some value. The first one is mutable, and the other one is const. The first one will go to the data section, and the other one will go to the read-only data sections. If I had a look to the flag, read-only is not writable. Okay, makes sense. And I can have a look to the content of this section with objdump, and you find this 7 number you had here. std vector, even when it's declared and initialized with an initializer list, my initializer list is a const array, so it goes into the const section. My variable is 0 initialized, so it goes into the BSS section, and I have some code that is executed at startup, and that's why I have this text.startup sections. Okay, so BSS section, it's a section full of 0, and so the only thing that matters is its size. So it doesn't take size in the binary, it only takes size once loaded in memory, and it only contains 0. So that's why there is the no bits flag. It's writable, and it takes some size in memory. And so the initializer list that was used to initialize the vector is in the read-only data section. That's where you see this CppCon stuff. Move on. There are a few not very useful but funny sections. You've got the comment section. And in the comment section, you've got a comment. This comment, if you have a look, it's some information about the compiler I used to compile this code. So it's leaking information. If you're using, for instance, an obfuscator, you may not want to sign, I have been protecting my code with that particular compiler. Okay. Funny enough, comments are mergeable, which means that if you have two comment sections in two different object files, the linker will just merge them. Okay, it's different from the conflict we had with the symbols. So there are plenty of sections. Some of them are linked to some aspect of the language, and some of them are there for bookkeeping, to help for linking. And they have different behavior with respect to the linker and the execution. One funny thing, you can update a section, the content of a section. You can use objcopy to say, replace the content of this section with the content of this file. So here, instead of the GCC signature, I just put a happy comment. But you could also use that to update data sections, code sections, to do whatever you want, and I don't want to know where you do that, but it's still funny. You may have heard about link time optimization. Link time optimization means you compile, and when you link, everything is happening. So there must be a way for the compiler to pass down information down to the linker. And to do that, they are using sections, and we're going to have a look at that. So I'm not a GCC developer, but still, I compile with link time optimization. I get my object file, and if I look at all the sections, I have plenty of them. Okay, and their name makes sense in some way. It's probably related to how link time optimization is implemented in GCC. But let's have a look to one of these sections, main like the main function in my hello. I'm trying, so objdump tells me it's okay, it's assembly code, but not. Quickly I find this bad, which means I have tried to disassemble these bits, but obviously it's not x86. Actually, it's a Gimpel. So it's the internal representation that GCC used to pass down information to. It's higher, as far as I understand. So I'm more comfortable with Clang, so let's do an example with Clang. I'm compiling the very same file with link time optimization, first line, and I'm calling readelf. Oh, it's called .o, but it's not an elf file at all. That's the wrong magic. So let's ask file, and file tell me it's LLVM-IR. Okay, great. So I'm disassembling this file, and I've got this LLVM-IR. You may or may not be familiar with, but I am. So I've got all my stuff. That's the main function, and I'm calling putS. Okay, so the way link time optimization is implemented in Clang is compile your code to LLVM-IR and pass this down to the linker. And then the Gold plugin will be able to gather all the bit codes and create one single file and then optimize it. That's full link time optimization. That's not how FinLTO is implemented. Another bonus. There is a specific flag in Clang called embed bitcode. Why would you want to embed bitcode in your ELF file? Well, ask the Apple guy, because whenever you submit an app to the App Store, your app is compiled with embed bitcode, so they have access to the bitcode instead of the assembly. God knows why. Here, they are both. But they don't use ELF. Yeah, but it also works. But you can have ARM on app. macOS, yeah. You can't run any ARM code on some Apple device.
It still uses Mako for iOS and watchOS as well.
Okay. But still, they are embedding the bitcode, so the same applies even if the binary is different. The binary format is different. So if I call objdump on this object file, I have these two extra sections, LLVM-BC, bitcode, LLVM-CMD, command, like command line. So I could use objcopy with this specific dump section argument, which tells the content of this section will be dumped here on SD out, but you could save it into a file. And so what it prints, it's the command line that has been used in Clang to generate this bitcode. And if I dump the section LLVM bitcode into a file, then I can disassemble it and I get back all the LLVM-IR. Okay, so it's okay to find the way back to how it's done by Clang. And it's actually pretty simple, but it can give you a hint. If you want to embed stuff into your binary, just create a section and put your data in a data section, not a text section. And you can put anything you want in it. Debug information. If I compile with -G, and I have a look to the sections, there's all this debug information that lies in different sections. If I have a look to one of them with objdump, then there's some text, some Mongol text. Okay, so that's all the strings used by the debug information, probably with links from the other section to this section. If I use readelf to dump the section, I have this specific flag, debug dump, and then it will decode the dwarf format for me, and I have this representation of the debug information. I'm not an expert at all in debug information, so I can't tell you more, but it's another section with its own format, and if you know how to decode that, you can take advantage of this information. GDB does. I don't. So it's only sections. If you're running a Debian system, you may have met this case where you've got your package, but it doesn't have any debug information. So when you run it in GDB, you don't have access to the symbol names, and you need to install an extra package that holds all the debug information, so that if you don't need to debug, the memory footprint on your disk is lower, and if you need to debug, you install the debug package. So that's, once you understand this section stuff, it's easy to understand how you can generate or split this information. First, you've got your binary compiled with -g. So that's foo here. And you obfuscate, so you copy only the sections that are debug sections into the foo.dbg. So that's my debug information, and I can ship them or keep them at home, and if my customer has an issue, I can get the core file and debug it using my debug information, but I don't ship the debug information, for instance, as a very low anti-reverse technique. Then I strip the debug information from my binary, and I can, if I want, add a link between the two. So it's just a reference. It does not put the content back. So that's how you can do the inverse of strip in some way. Exceptions. Exceptions are complex. They are complex at runtime, and they are even complex in the binary format. But basically, whenever you see something that's called EH frame, you've got something used to handle exceptions. There is a specific format in this section that describes all the call sites. It's actually a big source of information. Some friends, some colleagues of Quarkslab has been using the information that are contained in the exception frame to recover all the function pointers, the start and the end of each function, which is very helpful when you try to disassemble an object file. It turns out that even when you compile C code with GCC, no reference to C++, you will still have this section, because your C code at some point may be calling C++ code that has been exported. And so having access to the unwind information is useful. Instead of a crash, you will have something a bit better. It also helps for debugging, so it's always included. I tried to remove it completely using all the flags, no except, remove this section, and I failed. So it's not because it's impossible. Yeah.
You had to provide an option with no unwind tables.
I tried that, but the section was still there.
It's maybe because of linking, because it collects all.
Yeah, it was smaller. It was smaller, but the section was still. I wanted to remove the name, you know, in the header, and.
Maybe you use some such libraries and the linker merges all of this.
No, even on the object file. So it was too early to have that.
What was the question again?
Sorry. The question was, my inner question was, how could I remove this frame from my object file? And I tried a bunch of options, and I failed. Even with strip, you can say, remove this symbol, remove that, and...
Strip doesn't have the options for it. You should be able to do it by objdump if you wanted to remove the sections.
Yeah, probably, but maybe it won't load.
And you can turn off asynchronous unwind tables when you compile your object with GCC, and it should remove the EH frames as well.
Okay, so I've tried part of that, but not all of that. Thanks a lot. You also have this specific symbol, the GXX personality, and it's also part of the exception handling process, and I won't dive into the detail because I don't know them enough. Right. RTTI. Here I have some inheritance with a virtual destructor, a dynamic cast, so I need type information, runtime type information. And again, if I have a look to the symbols, I have this extra symbol, type info for bar, type info for food, the name, and so on. If I had created the diamond of def, I would also have a virtual table, and it's another symbol that holds information about how I should construct my object while I'm into the diamond inheritance. So every aspect of runtime information has its own symbol, its own table that is used at some point. It's just read-only data information about function pointers, offsets, but everything is in the object file. Relocations. You may have heard about that. Whenever you create a library that is a program that uses shared library, you don't know the address of the shared object. And so somewhere embedded into your elf file, you have an information that says, once you know where puts is, just patch this information, right, in the good place in the binary. It's like an embedded way to do a poke, that is, modify someplace in the binary. So if I had readelf for the relocation information, I've got a table, and it says, okay, this offsets here, so that's an offset in the binary. So at that point, I need to put the value of puts. And if I have a look at my binary at that address, I've got a 0. If you decompile a code and you see something like call and then 000, it's because it's the target for relocation. It turns out that there is absolutely no verification about the target, which means that if I'm using the obfuscopy replace content with that, I could create a binary that, when it loads, will patch itself and change whatever location in the binary I wanted to whatever value I wanted. Okay, so that's kind of anti-static analysis trick. I did not set up that, but I know it works. Some more thing about static initialization. I have this first object, which is built before the main, and its constructor is not trivial. So before I run main, I will have first that appears on my terminal. If I compile this, and I do an objdump, then I will see this new symbol, static initialization and destruction. So this function is an artifact that is part of the initialization process of the binary before main appears. And it's also when you load your library, if I'm generating a dynamic library, this function will be called. Actually, if I have a look to this specific function and disassemble it, the only important thing is here. I'm calling foo, the constructor of foo. So in this function, I have the constructor of all the objects that are created at static time, which is not context time. So one other thing that comes from C++, and you can track it down. You could track it even further, but that's where I ended my quest somehow. If you've attended to one of the security talks we had this morning and Monday, they were all using Stack Overflow and then executing some code that has been put into the stack. And this only worked because they removed this particular information, which says the GNU stack, so my stack, is only read and write and not executable. Okay, that's a protection. The stack is not executable and it's written in my binary. using all this knowledge, you could want to shrink your binary. That's something C++ developers are looking for, smaller binaries. So on the first line, I compiled with G++, my random code, and then it has a given size. If I ask to strip, I could use also the -s flag, which asks for stripping. -WL means pass down this flag to the linker, and then the linker will strip. It's smaller. I've removed the symbol table. I've removed the debug information. There was no debug information there. So, or I could use -OS for small. So find a better compromise between speed and size. It's slightly smaller. Turns out that for Clang, -OS is roughly equivalent to -O2. There's no, last time I checked, which is 1 year ago, so it may not be correct anymore, there was no specific pipeline for small size generation, small binary generation. But still, Clang generates slightly smaller. It's because it's a different optimization pipeline. Then I can strip some sections. The GNU version doesn't matter. The build ID doesn't matter. The AB attack, the commands, the GNU hash. I tried to remove that, but everything is not removed. And then I have a slightly smaller binary. And I tried to remove other information, but some of them prevented removing them prevented the binary to execute, even if it's not the text section, obviously. So that's the end of my talk. So I've begun in Elvish. I should end in Elvish. Anar Kaluva, Tieliana. I'm not sure of the accent, I have to admit. So the takeover is that most of the time you don't care. C++ gives you the right abstraction, and you don't need to understand what's under the hood. It's like driving a car. You don't need to know how the engine works. But sometimes you've got an issue, and then knowing the internals can help. Okay, so to have a look at the internal, you need tools. So if you're in the Linux world, NM to access the symbols, readelf to have complete information, objdump if you prefer its command line, and if you want to access to the content and to disassemble it, and obfcopy if you want to do dirty stuff, manipulating sections. And that's the end of my talk. If you have any question, feel free. Yeah. So that I don't have to repeat the question.
I suppose it's worth asking, templates then as well. Templates defined in headers that are encountered multiple times, I'm assuming are mangled the same way, and they're all weak?
Yeah, they follow the one definition rule, so they are marked as weak, and they are mangled, just like any C++ symbol.
Sure, and then if I had some other developer on my team that's within the same namespace and is defining templates in .cpps, because they're only specific to those particular translation units, and then I make a template with the same name somewhere else, when they meet each other, they're mangled differently, I'm assuming, because of their location in files, even if they share the same name, or will they perhaps step on top of each other?
The mangling does not depend on the file you're located in.
Okay, well, I was just trying to figure out how that would be resolved. I was presuming there was a way. That was my only guess.
I don't think there are, I think they have global visibility, and so there will be a conflict.
Okay.
So to assert that, you could force the instantiation of a vector in one file and force the instantiation of the vector in another file, and you will get a conflict, for sure.
Fair enough. Thank you.
So I saw a slide. You're shrinking the code size by removing all the sections. How this will actually affect the performance of the code?
It doesn't affect the performance.
It doesn't
give you smaller binaries, so it's faster to download, or it matters for a package maintainer, or for embedded system probably.
Okay.
There is a very good series of posts about trying to get the smaller binaries that says hello world. So it has to get rid of part of the libc and so on, directly calling, directly making system calls. It's a hardware from that. This particular example could be shrinked much more, but then not using simple command line flags.
Mm-hmm. Okay.
So I was about to make a comment about those simple command line flags to shrink it further. These still include padding between pages. So that's probably the reason why you have a size of slightly over 12K. It's just 3 pages with a little bit of padding in between. Mm-hmm. You can get the compiler to emit the padding, and that will get you in the executable in the low 1 kilobyte range. And to go beyond that, you need to go and try really, really hard.
Okay.
And that is just a compiler flag to disable the alignment.
Any hint about the look of this flag, or a keyword that would help to?
I'll have to look it up for you.
Okay, I will look.
As far as I know, you don't even need any section in an executable file. You just need the program headers.
Yeah. The content of the section is still there, but the section, the links to the section are not there. I mean, it's just 2 different views of the same content. So the content of the text section is still there, because that's your code, but you just don't have the addressing pointing to the different parts. So it removes the header.
Yeah, I meant the section headers.
Yeah.
Like you can remove every single section header.
Totally,
yeah.
Totally agree. Okay.
But if you do, it doesn't work with GDB.
Yeah, that's
Yeah.
right. You still execute the binary.
LLVM is fine, but GDB doesn't like it.
Okay.
A question about the function, if I remember correctly, DLCmit his flag RTLD next. Do you know this?
Oh, so the question is about DLOpen, DLC.
Yeah, DLOpen. It has a flag RTLD next, and it allows us to call another symbol, right?
Yeah.
And how it works with respect to
libdl is very complex. It re-implements the linker because it has to go through everything. So when you, my guess is that the linker at some point has a view on all the symbols, and it chooses the first one depending on different rules, but it can still goes to the next option. So as far as I know, when you're looking up for a symbol, you first look into the libraries that are in the library path, and then in the LD preload, there may be symbols too, in the air path. I'm not sure of the order. Then there are the air path, the one encoded in the binary, and then you go through all of that. And I think that this chain exists at some point, and DLNext can go through that. But I won't put my hand on that. I think that's how it works, but I'm not sure.
Okay, thank you.
It's possible in Linux certainly to pass a flag to linker requesting that multiple definitions be legal.
Yeah, I am aware of that. I never tried.
Okay, it works. I was hoping you might have some insights on how it works and why, and how do they decide which symbol in whichever case.
I seriously don't know, because I never understood why it's possible. So I know it's possible to pass a flag to prevent the error, but I don't know what happens.
You can get multiple copies if you're loading shared objects. You usually don't wind up with it if you compile a binary. But if you have 2 shared objects and they depend on a symbol, but maybe from a different kind of library, then you can end up with each shared object providing its own copy.
Yeah.
And then the linker just picks one, and your program crashes, and you're sad.
Sometimes it does not crash.
Yeah, that's right. Sometimes.
Thank you.
You're welcome. There are plenty of subjects like version scripts or linker scripts that we could have spoke about, but there are plenty of things to discover in that world.
One question about your that you told that you had frame section when compiled with fno unwind tables. And did you compile object file or executable file?
When?
What was the output of your compilation, object file or executable file?
At what time? For which example?
For example, with the frame section. If you compile an executable, it's absolutely legal because it's implicitly linked with some static libraries. And it merges.
So in my example, that's only object file.
Yeah.
And I think that when I tried to remove it, I went down to the executable.
And even if you provide the fno unwind tables argument, right?
We will
you
try.
You still have this section in object file, right?
Yeah.
Okay.
Any other question, remarks, advice, knowledge to share?
Can you comment on the names of functions and variables that starts on the underscore after you?
So he wants to know more about mangling. So there is a specification on how you mangle stuff. And so in the mangling, you have everything that you need to resolve an overload. For instance, the return type is not part of the mangling. The constness is part of the mangling. Number of parameters and so on are part of the mangling. Non-instantiated templates don't link to any symbol, so they are not mangled. Namespace is part of the mangling. Template arguments are part of the mangling. Whether you're a class or not, it's also, so a method or not, it's part of the mangling. The object type, I'm not sure of that.
Basically everything that you need in order to be able to print the original signature is part of the except for the return type. Yes,
yeah, I think that it's better to understand that everything that is needed to distinguish two C++ variable is part.
Well, I mean, you can just do it in Pythran in that case, but
yeah.
So what happens if some developers will use the underscore and variable name as a private variable in class? Will they have a chance to have a really nasty linkage?
The only people that are allowed to do that are a compiler developer. If it's underscore with a capital letter, okay. So if it's a lowercase letter, then it's not part of the mangling, so it's not a reserved prefix. And if it's a capital letter, if it's in a member, then there is already a prefix for the class. So I think it's okay.
It's UB.
That's UB too.
If you have anything with underscore and a capital letter as a non-system developer, it's
yeah, as a non-system developer, but it still works for GCC. So or can.
It's not going to punish you. It's not actually going to punish you.
Sorry.
But it is still UB.
It's valid for the STL implementation, right? Okay. So the compiler knows something at that point.
It's not going to punish it because it might be the standard library actually doing it.
Mm-hmm.
But as a user, if you do this and it breaks
you have no
and
guarantee.
burns down your house, don't complain. You did that to yourself.
Only after 2 or more underscores, or just even one underscore?
It's single underscore in a capital or 2 underscores.
Full
Yeah.
single capital at whatever means it.
Yes, yes.
In other words, don't start things with underscores. It's not worth it.
Fine. Have a good day.